Hello, and welcome to this webinar where we will go through the latest developments in ANSA and Meta for CFD applications. After the presentation, we will have a live demo of the key topics. My name is Nicholas Christodoulou, and I'm part of the CFD team of Beta CAE Greece. Let's dive now into our new features. We will start with meshing. ANSA can now produce a CFD type mesh on tessellated STL data by following the exact same method as when using CAD surface data. The STL mesh is used in a batch mesh session, and the result is almost identical to the mesh that would be produced if we were working on geometric faces. As you can see here, the result on top left, the STL tessellated result, and the CAD data on the bottom right. Almost identical. Moving on, there are significant improvements in our mixed mesh CFD algorithm, especially for aerospace meshing. Using feature recognition, ANSA can apply an isotropic mesh treatment on leading and trailing edges, and at the same time produce zones around these features with quad elements. Based on our experience from the aerospace sector, we have concluded that the quad dominant mesh is very suitable for CFD, yielding less elements and more mesh flow alignment. In our new version of ANSA, the user can decompose the domain in order to speed up the volume meshing process in multicore mode. This is supported for the Tetra algorithm, and the improvement in speed is significant for meshes with high amount of elements. Another significant improvement is the new architecture that allows the generation of billion cell meshes. This is applicable for all volume meshing algorithms, standard, polyhedral, and hextream. However, at the same time, ANSA manages to maintain a low memory footprint as low as 0.3 to 0.4 gigabytes per million elements. Regarding the boundary layer generation now, on the left of the screen, we can see the improved smoothing of layers that are generated in aspect mode in order to avoid bumps. Top left is the older version, and bottom right, as you see, is version 22. On the right of the screen, we can see how the smoothing of layers, which is taking place in several steps, allows better layer coverage and mesh quality, even in cases like this where high proximities are present. Regarding now cavity remeshing, the user is now possible to replace a meshed area of the model with a new unmeshed geometry. The unmeshed geometry must, however, belong to PIDs that are already loaded in an existing surface mesh scenario, so that ANSA applies the specific mesh treatment to the new geometry. Of course, after the surface mesh, ANSA will proceed with the volume meshing. Cavity replace can now also be applied on hexa interior mesh without requiring a buffer zone as in the past, where the hexas of the cavity need to connect with the outer volume. Now ANSA can generate directly hexas that connect with the outer volume, and this creates a nicer hexa-dominant mesh with less volume elements, since the buffer zone is no longer needed. You can see in the middle image how the buffer zone was at the past, and now how on the right there's no buffer zone anymore. Regarding the size field refinement zone, there's a new option for sweep refinement along a curve, as you can see here. to model a vehicle during a turn or other applications with similar needs. And this is the result. You can see how the refinement follows the curve, and even the mesh starts from fine and gradually grows bigger based on the settings that are applied here. Okay. Still at the size field functionality, there's another enhancement. A new refinement type called adaptivity field has been introduced. This functionality, what it does, it can read the prescribed and externally calculated size field in the form of X, Y, Z ideal cell size. And then the meshing algorithm can respect the cell size values and generate a mesh following these sizing rules. Here we can see the build size field. You can see the colored elements, and the coloring is based on the cell size read by the solver output. And here is the actual mesh built. You can see the refinement areas at the wake and at the front, even at the stilts here. In the Off Inspector tab, it is now possible to plot histograms based on the selected quality criterion here. And in the Hexablock menu, it is now possible to create 2D boxes for 2D structural mesh. Now, this could be done with our classic mesh abilities, but if you use Hexablock, the 2D structured mesh, it's much easier to be produced and also modified, maintaining an excellent mesh quality. To do so, to maintain a great quality, there is a new function for advanced elliptic smoothing of the surface mesh. The user selects the 2D boxes to smooth the mesh. Then the user selects the boundary condition type. Here you can see to be applied at each selected feature line to control how the mesh will behave at the boundaries. The relaxation factor controls how fast the mesh changes at each iteration, and iterations control how much the nodes will be moved from their original position. Similarly, there's the function for volume mesh smooth, which is the equivalent elliptic smoother for Hexablock volume meshes. Another enhancement in Hexablock is the new function Templates Turbomachinery, where this template will automatically generate box topologies and mesh them. It can be used currently on axial turbomachinery geometries. Let's move on now to new features of the morphing menu. A new algorithm in direct morphing called Form can help the user to change the shape of models interactively. The user can place the middle axis system without morphing being applied, and then can use the corner axis systems to bend, twist, taper, or extend the model. It is very handy for cases like the one shown here, a wing. And you can see here the result. Still many options available, like the quadratic interpolation, which ensures tangency continuity. Preview should be enabled for interactive morphing, and save can be used to save the setup as a direct form parameter. Let's proceed now to the solver setup. In ANSA, in already the versions that are uploaded, the older versions, a rotating interface can be automatically created to generate a moving reference frame or rotating zones. Now, in the new version, the resulting interface can be flat, as you can see on the right image. So in the past, the user would specify the offset only, but now if you activate this flag, the user can produce a planar external interface, which is handy on some occasions. There is a new icon button to access the deck report mesh statistics reporting tool. Now it is enhanced with reorganized information and histograms. There's a new GUI for the setup and edit of EVI schemes, EVI solution, EVI options, transport and thermophysical entries for OpenFOAM. The user can change the settings from drop-down menus, as you can see here, and click on Update Text or edit directly the text manually. ANSA now also supports the setup of a conjugate heat transfer case with fluid and solid volumes and mapped wall type properties between them. The definition of separate EVI schemes, EVI solutions, EVI options, and thermophysical properties are supported for every fluid and solid region, as can be seen on the image here. Mapped wall for each fluid-solid interface, and also different settings for every fluid and solid region. For the quick setup of CHT and compressible cases, a new graphical user interface is developed where the solver settings can be easily selected. ANSA will output, of course, the whole OpenFOAM tree structure. Let's move on to the new features of the post-processing meta. But first, let's have a quick look at all formats that are supported by Meta to see if there is one that fits your needs. And let's move now in this nice feature where it is possible to unroll a cylindrical isosurface. In this way, better inspection, of course, is possible. And how this works, the user selects new from rotating region, selects the rotating PID, and then types a radius where the cylindrical isosurface will be created. Finally, there's the option to unroll the cylinder, as you can see here, where the user can control if he wants an absolute flat surface or it wants to be partially rolled. Meta is also able now to display correctly the front and back side. This means the wall and the shadow wall of duplicate baffle zones. In other words, zero thickness faces. Another cool feature is now that it is possible to calculate and visualize lines along separation and attachment areas. Here, the separation line is colored red, as you can see, and blue is the attachment line. Meta can now calculate some predefined results when the solver does not provide them. These are the boundary layer height, the skin friction, lambda2, and the Mach number. And another very handy tool, especially for wing design, is the quick 2D plot of a section. So the user creates a cut plane and then with right click, selects the plot section. A 2D plot of the selected result will be created, like pressure or pressure coefficient versus distance. This can be coupled with an animation, as you can see on your screen. Finally, a nice feature that is that in PID list or in statistic window, now there's the option to right-click on some entities and select histogram. In this way, we can easily identify, for example, the Y plus range and see if it satisfies our requirements. Thank you for participating in this presentation, attending this presentation. We have now concluded the major latest developments in ANSA and Meta for CFD applications. And now we will proceed with a live demo on the hot topics. Let me start with ANSA and show you how the quad dominant anisotropic mesh is created for aerospace applications, but it can extend to any type. So first here we can see a typical aircraft geometry. I can switch here to feature mode, feature drawing mode, and you can see different areas of the model are colored. On the top left, you can see the legend. So here the trailing edges are brown, some sharp edges are colored pink, and you can see in blue the leading edges. So these are automatically identified by ANSA. And then, based on the recognition, specific mesh treatments can be applied. So if we access the feature manager, we can see all the features in a list. If you click, you'll go to the respective feature, and it has a certain ID for special perimeters, for trailing edges. Next step would be to go to the batch mesh and set up our batch mesh session, where we will go, for example, and mesh the wings. And if we switch to the features tab, you can see that we have a specific mesh treatment for every area, trailing, sharp edges, leading edges. And this is visible if we see the mesh. And you can see now how nice is the leading edge resolved using zones and quad elements. And the same stands for the trailing edge. You can see how nicely it will blend with the rest of the mesh, and the mixed mesh type can work very nicely and be oriented to the fluid flow. Next, let's have a look on how we can mesh now, change the mesh of tessellated data. So on the left, you can see a mirror that is actually is using tessellated data. It's only elements. And the same mirror using CAD data, so faces. So now it's possible just to switch to the batch mesh, where both mirrors are under the same session with the same CFD parameters for the meshing. And we can just press run. Let's give it a couple of seconds. And the end result, you'll see that will be almost identical to the CAD surface. ANSA will do refinement on curvature and apply the CFD meshing rules on both models, even if they have so big difference in their definition. Couple more seconds and it will be finished. So this is very handy in case that you have tessellated data. You could do some pre-treatment actions, create a watertight model, remove the noise maybe using ANSA tools. And then you can finally convert this STL mesh to a nice CFD mesh, as we will see right now. So it is completed. You see that there are some feature lines recognized automatically by ANSA. And if we close these lines, let's inspect the two models and see. You can see here there's refinement as well on both of the models. And the resulting mesh on STL is of excellent quality. Let's move on with the rest of the demo files. We will go to replace cavity. And what we are going to see now is actually we're going to replace a mirror at the beta car, as we call it. In the past, you could do so, you could replace parts, but the parts you could bring inside the model should have surface mesh. This was a prerequisite. Now, the new feature is that you can replace parts that are actually unmeshed. And the only thing that is needed is that the parts that you are going to bring inside should have corresponding PIDs that will automatically be filtered inside the batch mesh. This is needed because ANSA needs to know how it's going to mesh the new parts that you have brought inside. So it will put them in the respective session in the batch mesh and use those settings. So let's have a look. So the model now that is going to be drawn by ANSA has already surface, layers, and volume mesh. It's completely meshed. And let's see how we will be able to replace the mirror. Let's give it a couple of seconds. This is a very handy tool because it's easy to do a model update on specific parts, and you don't care about nothing else. You will just use the replace functionality, and ANSA will do the rest. So what we see here, we see a mirror that has layers and volume mesh. Now there's a cut plane, but it's finite, just to focus on this area. Let me show you that actually all the model is meshed and we can visualize it with a cut plane. And what we will do now, so here, this mirror is in this vehicle session for the surface mesh and in the default session for the layers. So we need to make sure that the filters are properly created and will filter the new part that we are going to bring inside. So let's use macros replace. We can use the part selection to select all the mirror, confirm, and now we will bring an unmeshed mirror. We can press OK using the default settings. And now what ANSA does, it removes this mirror. Of course, it digs a hole in the volume mesh, and it brings the new mirror inside. It searches inside the batch mesh to see where this part should be filtered, these PIDs, and then it will start applying the mesh, starting from the surface mesh, continuing with the layers, and finally the volume mesh. So there are two new things now in this functionality. One is that we can replace an unmeshed face, a meshed with an unmeshed face. And the second thing is that you will see that the volume mesh does not require anymore a buffer zone for hexadominant meshes. For tetras, it was the same. You will just build tetras. But for hexas in the past, ANSA would require to create a tetra buffer zone in order to connect the new hexas with the old ones. But now it's possible to do it from start with hexa and properly connect it with the rest of the domain. Okay, let's give it a couple of seconds. We will spend most of the time of this webinar in the live demo, since it's much better to see actually how things work, and you can see now there's a process ongoing, and on a laptop, of course, that's why it takes some seconds more. Okay, maybe while this is working, we can switch on another demo case and give it some time to be completed, and we will come back to that. Okay, the third demo that I would like to show you, the fourth actually, is the adaptivity refinement. Oh, no, not yet. Okay, so it's the adaptivity refinement where you can use, the user can use a format of a CSV file or text file of the format XYZ and ideal cell size. We can see it here. So XYZ coordinate and the ideal cell size. This output is based on the solver, and ANSA can read it in a size field, as you can see it here. So the adaptivity field, you can read the file, and then you can press on inspect in order to inspect actually how this file is represented inside your model. So let's bring it inspect. This will also take some time. So in the meantime, let's go back here. You can see that ANSA has proceeded with the layers generation, which is completed. The total solids generated are 70,000. And now the volume mesh is being processed, and we have our new mirror. So let's have a look. The boundary layers are properly generated on the new mirror, the surface mesh, the same. It has a nice connection with the rest of the model. And you can see there's no buffer zone around it. And let's actually inspect that by deactivating the finite plane. And let's have a look if we move it. How the volume mesh is properly built around the new mirror and the layers. And there's no buffer zone, as we said already. Okay. Let's have another look now. While the size field is being inspected, I'll show you right away. So this size field functionality supports also the traditional size boxes, but it has expanded its functionality to new areas. And one of which is the one I'm going to present now. And it's actually, if you have something that you want to refine, like a vehicle, like a car here, or maybe a leaning motorcycle or anything like that on a corner, now the size field can take this curve as an input and can sweep the refinement area across this line. So you can invert the direction if you want. So the sizing rules will be applied from start to end. However, now we want it differently. And here, as you can see, there's the offset, there's the sweep curve ID, and there's an offset at the sweep end. You can define, you see that it's a different offset at the start and at the end. You can define a variable size of refinement. So at the sweep start, the maximum surface length is 25, but at the end, the maximum surface length grows to 100. And you have a different growth rate at the offset direction and at the sweep direction. The same applies for volume mesh, of course. And let's visualize it now. So visualize is not building. Building will read the result, the settings, and create the size field. Visualize is just to see what was previously built. And you can see now with the different fringe colors how the refinement changes from a very fine mesh of 25 around the car and gradually grows into 100. That is the final mesh refinement setting. And if we see the actual mesh, you can see the smaller element length that is applied here and how it gradually grows to a bigger one. Okay, let's move on. Okay, let's move to the hexablock now. Still I have running the inspect function here that I'm going to show you. But in the meantime, let's see the hexablock functionality. What we see here is 2 airfoils that have quad elements. And with yellow lines, these are the 2D boxes. So you can see we have boundary layers on both airfoils. However, we have a mesh that is not so nicely smoothed. There are some refinement areas here that could be blended in a better way. So if we go to the hexablock menu, we can access the smoothing algorithm of the shell mesh. And what we see here is first it will ask to select the box faces. Let's select all of them. Next. Now it has identified the feature lines automatically. We can modify them, but the default works nice. And now we have boundary conditions that can be set up for different feature lines here. So we could say that we want fixed or orthogonal boundary conditions on these airfoils. This means that the boxes will not move, but it will try to generate layers that are orthogonal to the feature lines. And we can also select now the rest feature lines that are outside of our domain. And if I activate this flag, we can see now the different options. What I would like to do here, these feature lines, I would like to have them as sliding. This means that we give the freedom to the smoother to move the boxes, slide them, and slide the mesh apparently, in order to have a better result. So here, these are separated in groups, and we can see the different settings. So in group 3, I would like to have orthogonal layers 4, and at the back as well. Okay. The relaxation factor, I will leave it 0.4, so it can move little by little in every iteration. So I'm on the safe side. And we can press run and see the smoothing action taking place. So for generating structured 2D meshes, there are also other ways in Anza, but by introducing and using the 2D boxes in your process, you'll see that you'll benefit a lot in terms of speed and quality, especially if you're going to change the settings and you want to reapply the meshing. So now the smoothing is complete. Let's have a look. You can see here 1, 2, 3, 4 first layers, 2D layers are orthogonal, and then it tries and smooths the rest of them. The same stands for here, because we imposed the orthogonality of the 4 first heights. You can see here that the mesh has been sliding on the edges, and it's better visible if I show old and new. And here, let's show old and new. And you can see how nice the blending action takes place. So if we finish, we can have a look of the resulting mesh. Let's hide this as well. And you'll see how nicely everything is blended. Areas like these that have a bit big elements are based are due to the spacing here. So by changing the spacing on the surface mesh, these areas can be improved a lot. Overall, it's a very fast and efficient way that can give you a nice result. Still in the Hexablock menu, let's go and see our new template. So let's see the model. So this is turbocharger, and we can see here we have one blade. Let's switch to PID view, and we can see that it has a rounded leading and trailing edge. There's no fillet at the hub, and there is a small tip gap at the shroud. Very small tip gap here. Okay, so there's a new template here that's called Turbo Machinery. However, before jumping into this application, first we need to do some actions. First is to change the tolerance mode to extra fine, because there's really high accuracy needed in order to respect the tolerances of models like this. Then we need to make sure that our properties, our PIDs, are properly named and categorized. So here you can see there is a blade, inlet, shroud, outlet, hub, and tip. These names are the ones that ANSA will search for when filtering and generating the template. And we have also two sessions, one for leading and one for the trailing edge here. Two sets, sorry, a leading and trailing edge set on the cons. And how this works, actually, we open the Turbo Machinery application. We define the number of passages. The rotation axis, you can pick it. Already it's the z-axis here, 0, 1. And now let's provide the settings. There is a small tip at the shroud. The leading edge is rounded, the trailing edge rounded, and there's no fillet at the hub. So as I mentioned before, here you see that these are the actual PIDs that are inside the database. So by giving the correct names, ANSA is able to filter automatically where everything goes. If not, you can select the correct one from the drop-down menu. The same stands for the sets of leading and trailing edges. Then you define the mesh parameters. Mesh size automatic means that you'll just give your final element count that you want, like 400,000, or you can give a number of elements per direction, inlet to outlet, hub to shroud, and blade to blade. This allows even for more control on how the meshing will be done. Then there are different categories here for blade, hub, tip, and shroud refinement regarding the boundary layers, the first height, and the growth factor. Finally, you will define a fluid name, which it will create a solid property called fluid. And you can specify how many passages you want to mesh. You want to mesh only one passage, or you want the full model. Then ANSA will generate the shell mesh, the volume mesh, and will apply elliptic smoothing, but now on the volume mesh. Because this will take significant time, I have it ready here just to check the result. And let's have a look. So you see how the box topology is created and the mesh. let's let's inspect the boxes. You see how there's offsets to do boundary layers, all grids, etc. And if we have a quick look at the surface mesh, you can see how the result mesh is a nice pure hexa mesh that has been smoothed. Okay, let's go back to the adaptivity size field that we have pressed inspect before. So what we did here, we read the CSV file and we pressed inspect. And actually what I wanted to show you is that I did a mistake, obviously. And here, the mistake was done on purpose, just to show you that here the values were on meters, but we are working in millimeters, so a scaling needs to be done. Another thing you will notice here that the values used vary very much. Again, this is in meters. The highest value that the solver introduces is 17 meters, and the lowest is really, really low. And finally, another issue that using inspect, we find another issue is that here is only half of the model, but I have the full one. So what we can do, so the inspect functionality helps you identify these errors, let's say, these mistakes. And if we activate all of them, we can scale the model by 1,000, so it will be millimeters. We have a minimum length, so it will cut off some values of the Excel and a maximum length of 50. And now we can visualize it and see actually how this ideal cell size is colored on the volume area of the model. After we visualize, again, we will see if the settings are the ones we want, or maybe we need to change the settings and inspect again. So the visualization is here. Let me minimize this with middle click. And you can see here how the values are colored. I need this one in order to a bit go through the cut plane and inspect if these are the areas that I would like to refine. Okay. And if I activate the wire, you will see again the refinement in the front, around the stilts, and at the wake. And of course, this can be applied on the volume mesh as well. Okay, let me check that we have inspected, we have seen all demo files of ANSA. No, there's another one regarding the OpenFOAM. Okay, so let's quickly check this, and then we can spend some time to meta. So in every version, we support more and more OpenFOAM functionality. We started with just setting up quickly an incompressible case, then we moved on to Y+1, then we moved on to compressible and conjugate heat transfer, as you see here. So here it's an exhaust manifold, and if I activate a cut plane, you can see here the different zones. There's, sorry, let's move it like that. There is the fluid zone, there is the solid zone, and there is also the porosity area here in the catalyst. So if I move on to the deck, I can use setup CHT, and I get this window. where I can define the OpenFOAM version, the solver, the turbulence model, wall treatment, mesh quality. These are like setting up other OpenFOAM cases. We can specify the inlet PID. We can specify the outlet PID. Initial velocity, initial temperature, intensity, external temperature, and fluid temperature. Let's say we want 10 decomposed domains, and we will switch to regions. Here we have 3 regions now. We want air for the fluid. We want air still for the porous medium. And for the metal solid, we want stainless steel. We have a moving a porous zone here at the porous, so yes. And we can specify the coordinate system of the porosity, which will be 1 here, and we can specify values for the Darcy-Forchheimer porous model, and click on Setup Case. So the setup is successfully done. We can see that now ANSA has created 2 materials, one for air and one for stainless steel. And then if we go to the Advanced tab, you can see here that there are EVI schemes for air and stainless steel that are different, EVI solution, and the thermophysical properties. So now you can output the case directly, and ANSA will create the folder structure of OpenFOAM. Let's move to Meta now. First, I'll show you how now it's properly colored, properly drawn, the very thin faces of this blade, a 0 thickness wall, as we call it. And what is nice here is that if we go to the isosurface, we can create a new cylinder from rotating region in the fluid MRF. We can specify a radius of 0.1. And after this is calculated, we can go to the Advanced tab and unroll it. So now it's far easier to inspect these regions, and the rolling action can be done and undone or being done partially. And let's close now with a nice cool feature that we've seen in the presentation. We have a flow here, an unsteady transient flow around the cylinder. And now it's possible in Meta to generate a separation and attachment line. Sorry, let me do it again. New separation attachment line. I select the cylinder that I want to be drawn here. We can change the colors. Let's say separation can be red and attachment can be maybe blue. And let's switch to a nice perspective view. And you can see here the blue and the red, the attachment and separation lines, and how this can oscillate now, for example, during this nice fluid flow. So thank you very much for participating, for attending this webinar.